Good morning, POE students. And today is covering Friday, April 24th lesson on free body diagrams. All this stuff that I'm going to show you can be found under modules. Under modules, there will be this video. There is a link to the information in your electronic textbook on my.pltw.org. There's a link to an activity that you can do. I'm not grading. There's also a link to a PowerPoint, which I recommend that you watch, and underneath of that PowerPoint on modules are essential questions. You do not have to complete the essential questions, but if it helps you to take notes on important items and information from the PowerPoint, feel free to use that. And then there's an activity 2.1.3a, and the answer key to that activity is just below it. Okay, there is also a practice assessment on this, and then there will be one assignment that has to be completed by next Sunday night. Not this Sunday, but next Sunday night. Okay, all right, so let's get started today. Free body diagrams, and again, I recommend that we watch PowerPoints in PowerPoint format whenever possible, because there are animations in there that can help us. Okay, so free body diagrams, what are they? A free body diagram is a visual representation of force and object interactions. So simply put, all objects have forces that act upon them. Okay, so if you have a water bottle right now sitting on your desk while you're listening to this, there are forces acting on that water bottle so that it doesn't move. If it's sitting on a table, then there are forces acting on that table so that it doesn't move. If you're sitting in a chair, then there are forces acting on you. There are forces acting on the chair. There are forces acting on the floor. So everything that we have has some type of force that is affecting it in some way on planet Earth. Okay, so a force is a straight line push or pull acting upon an object. An important piece of vocabulary here, is right here. So a vector quantity, which we're going to get to after this unit, we're going to do force vectors. But a vector quantity has direction and magnitude. Okay, so forces move in a direction, and magnitude just means amount. Okay, so vectors, a vector quantity, we call it a vector, has both direction, so maybe like down with 10 pounds of force, or up with 100 pounds of force, or to the right with 10 pounds of force. It has direction and magnitude. We illustrate the direction with an arrowhead, and then the magnitude is illustrated by a length of the arrowhead. So for example, if I had an arrow that was this way, like this, and I said that was 5 pounds of force, and then I had an arrow that was twice as long, I would label that 10 pounds of force. So the length of the arrow indicates the magnitude of force. If I didn't label the forces, and I just drew an arrow, let's say, in the opposite direction, but smaller than this arrow, right? Shorter than this arrow. Then basically what I'm saying is there are two forces there, right? There's one going to the right, and it's greater than the one that's going to the left. How do I know that it's greater? Because the arrow would be smaller, okay? Okay, so moment. Moment is the twisting effort about a point or axis when a force is applied at a distance. So we've kind of already talked about this year, and so for example, we said, and we're going to see this picture, I believe, again, but if we have a bolt and then we have a wrench, so we saw this back during Simple Machines, okay? And if I push down on this wrench with 10 pounds of force, and I tell you that the wrench is 1 foot long, then moment equaled perpendicular distance times force times force. So perpendicular distance, that's just a perpendicular sign. So basically I'm trying to draw a right triangle. Perpendicular distance times force. So I have a force that's going down with 10 pounds, and I have a distance that is perpendicular to that, right? My force is down, and my distance is perpendicular to that. So I have basically 1 foot times 10 pounds, and I would have 10 foot-pounds of moment force. But what we're talking about when we talk about moment, okay, is the amount of force that the very center of this bolt is feeling. So that bolt is feeling all of this pressure. It's feeling 10 foot-pounds of force right on the center of that bolt. Okay, so that is the moment force. It is the twisting force that is being felt at the center of this piece. And what you see in this PowerPoint, get back over to it. Okay, what you see in this PowerPoint is it says that if it's going to the right, so we have clockwise and we have counterclockwise moments. Okay, so for example, here's the example with the wrench. Okay, more moment equals force times perpendicular distance. Okay, so we have a force, we have a distance, and that would be our moment. And we can either have a clockwise or counterclockwise. And we will come back to what that means, whether or not that's positive or a negative amount. And that we'll come to that later. Okay, so a free body diagram. All right, so as an important note to take with free body diagrams is that a free body diagram, so a free body diagram is a diagram of all of the forces acting upon a given object. Okay, so acting upon. So in other words, we want to know all of the things that are happening to that object. Not what that object is doing to other things, but what is happening to that object. So let's go back to our example of your water bottle. If I said, draw a free body diagram of the water bottle, okay? Your key here is to pay attention to whatever comes after the word of. So in this case, it's the water bottle, okay? And what we want to know then are what are all of the forces acting on the water bottle. So forces acting on the water bottle. Okay? So we'll come back to that in one moment. All right? So if we go back over here to the PowerPoint, it says a stack of 3 books, each weighing 5 pounds, is sitting on top of a table. Draw the free body diagram of the top book. So of the top book, right? Of. So I want a force diagram of the top book. Now, the important thing here is that we want to isolate whatever comes after the word of. We want to isolate that. So basically, and you'll notice that those books are labeled, right? DE, POE, and IED. So those books are labeled. So we're going to have to label them in our diagram. So diagrams have to have anything that is labeled in the original picture Okay, so we had a book called DE, a book called IED, and I believe a book called POE. Let's go back and make sure that it was in that order. DE, POE, IED. Okay. POE, IED. All right. Okay. DE, POE. So this is just the original, okay, the original picture, and it was sitting on a table, right? Now the problem said draw a free body diagram of the top book. So what you're going to do when you hear that of, remember I said to focus on the word that comes after of. So in this case, we're going to focus on the top book. So in your brain, what I want you to do is draw an imaginary circle around that object that comes after the word of. Okay, so we're going to isolate that object. So I'm going to go back over here and I'm going to just draw a diagram of that object. Okay, and I'm going to have to label it so that because it's labeled in the original picture. Now, the question, remember, a free body diagram is a diagram of all of the forces acting on the object. So what are all of the forces acting on this book? This book is just sitting still. Well, how is it sitting still? Okay, so we have some forces that are affecting it. And you've probably already guessed one. One of them is gravity. Okay, so basically we can go over here and we know that vectors have both direction and magnitude. So let's start here. So in my mind, I know that something is touching this book here, right, on the bottom of the book. So there's a force there for sure. So let's start here. I know that gravity pulls down on the center of an object. So we're going to label that force grav. Okay? Force gravity. Because it's pulling down on the middle of the book. But the book's not moving, right? It's not going down right now. It's not, when we look at it, it doesn't look like it's falling towards the earth. So what else is happening? Well, as we've noted, there's something that is touching this book, and it's the POE book, and it's pushing back up. So it is a normal force. So we call this force normal. Okay? Force normal. And a normal force is just when an object is sitting on the ground or like on a table, when it's sitting on something, it's the natural force pushing back up on it. So if you have your water bottle right now and it's sitting on your desk next to you and it's not moving, well, gravity is pulling down. So if your water bottle, let's say, weighs a pound of force, it's pulling down with a pound of force towards the earth, right? Now, technically, it's more force than that because we have gravity, but the water bottle is pushing down on the desk and it's not moving the desk. It's not pushing the desk towards the floor. The desk isn't falling towards the floor. The water bottle is not falling towards the floor. And that's because the desk is pushing equally back up, okay, with the same amount of force that the water bottle is pushing down. And so they cancel each other out. So if it was a pound of force down, a negative pound, and the desk pushes back up with a positive pound of force, well, we have zero force, right? So zero net force means it's in static equilibrium. It's not moving, okay? It's balanced, okay? Zero net force equals static equilibrium. So this would be the free body diagram of the top book. Now, let's go back and let's imagine that the problem didn't say to draw a free body diagram of the top book. Let's say it said to draw a free body diagram of the middle book, okay? So of the POE book. So we say, okay, well, I'm going to isolate in my mind the top or the middle book, and I know that something is happening to it here, and I know something is happening to it here. So let's redraw the object first, okay, that we're talking about of the middle book. So we redraw the middle book. And in this case, I know that the DE book is pushing down on it, right? Something is above it. So we could say, we could just say like force of DE, like force of DE book. And we could say normal force. What else is happening here? What else is happening here? Well, also we have the force of gravity. And notice um, I drew these to be equal here. Okay, I drew these to be equal. Okay, so let's go on in our PowerPoint. Okay, so sketch the isolated object, and they told you it was 5 pounds, actually. So what is the isolated object? The top book. So here's our top book. We're going to sketch the applied and normal forces. So when an object is in contact with and is supported by a second object, the second object can be replaced with a normal force, which is perpendicular to the surface of the second object. Okay, so all that's saying is when you have an object, so when you have an object and it's sitting on another object, it's being supported by another object, you replace this object with a normal force that is perpendicular to the surface of the second object. So perpendicular, right, to the surface. So normal force, that's important that we say that it has to be perpendicular, because let's say I had a ramp, and let's say I had a box sitting on the ramp. And the box, right, gravity always pulls down on objects towards the earth. So gravity is pulling it down, but the normal force has to be perpendicular. So force normal would be perpendicular to that box. Okay, it's being supported. So here in that example, the box is being supported by the ramp. So the normal force is perpendicular to that surface. Okay, good. So here we see sketch the applied force and normal forces. Applied force, weight of the top book, and normal force. Okay, now I replaced the word applied force with weight of top of book with what? With gravity, right? What is the force of gravity? Well, the force of gravity is literally a force that occurs, right? It pulls things down. So there's an applied force, there's a force being applied to the top book, which is gravity. So force of gravity is pulling down. It's fine if you label it here as applied force. The key is this. What you must do is when labeling this, okay? So when labeling this, I'm going to give you a couple of examples here. So we're going to do just that book, okay, the DE book. And I'm going to tell you a couple of different ways that you could label it, and they would all be correct. Because there's only really 2 rules to it being labeled correctly. Okay, the rule to labeling it correctly, the first rule is it must be in the correct, I guess there's 3 rules. In the correct location of object, must be in the correct direction, and must be correct magnitude or amount. So when you're labeling your forces, those are kind of the three rules. So in this example, they told us that we have a force that's going down, and that is a force applied, right? That's also can be referred to as force gravity. You can, in this case, because it's gravity is what's applying the force, but you could label it either one. They would both be correct. And it's going down, right? It's going to be going down, so we're going to have to make sure we draw that down. And then we have force normal, force N or force normal. You could write out either way, going up. So it would be correct if we drew a free body diagram like this, if we said force applied, and we said force normal. It would also be correct if we said force normal. Notice my arrows are the same length, and force applied or force gravity. We could label that. And then here I could say, oh, we've got force norm and force applied. All of those are correct. Why are they correct? Well, let's go look at my three rules. It must be in the correct location of the object. Okay, it's going to be the middle of the object. The centroid is where the force is happening here with gravity. Okay, so must be in the correct location of the object. So the center of the object, check. Must be in the correct, oh, I think I messed this up. Correct location. Nope. Nope, that's not what I meant there. Hold that thought. So it must be in the correct location, must be in the correct magnitude, and, oh, that should say direction. Sorry, correct. Direction. Okay, so this is correct. I have the applied force, or gravity, going down, and I have the normal force going up. So it's in the correct location of the object, it's going in the correct direction, and they're the correct magnitude. So my arrows are equal because the book's not moving, right? So what's pushing up is the same amount as what's pushing down. Well, let's think about why this one's correct. Does it meet these three rules? Okay, are these all in the middle of the object? Yes, they're in the middle of the object. Okay, must be in the correct direction. Is the normal force pushing up on the object? Yes. Okay, do I have that labeled? Yes. Is the applied force, force of gravity, so we could also label this force G. Okay, or you could label it weight, W, book. Okay, weight of book. And weight is caused by what? Weight is caused by gravity. So either way. And that is in the middle of the object, and it's going down, and it's the same length arrow as this one. So correct. And then look at this one. I have the book. I've labeled a normal force that's affecting the book in the middle of the book in the upward direction, right? Middle of the book, upward direction, upward direction, upward direction. And I have a force applied, or force gravity, or weight of book that's pushing down on the middle of the book with an equal amount of force, right? These arrows are the same length, an equal amount of force, and the middle of the book. So my arrow is going in the correct direction. It's labeled on the correct area of the book, the middle, and it's the correct length. So any of those three would be correct. I find this one to be the best one. I think it is the most intuitive, meaning it's the easiest to picture when we talk about this. Hey, something's pushing down on the book and something's pushing up on the middle of the book. And so I think labeling it that way is the best alternative. Okay. Okay, so moving on. All right, so we see that here. They labeled the actual amount of force, so they labeled it W equals 5 pounds of force and normal equals 5 pounds of force. And remember, that was because in the actual problem, they told you that there was 5 pounds of force somewhere. Yep, here they said it's each weighs 5 pounds of force. So they're labeling the actual amount of force, which is important. Okay, so in a problem, what you'll also notice are that you also have to label dimensions if they are present. So notice that the dimensions, the angles, they're all labeled. So this is different than this, right? So we're not talking about the book anymore. This is something we'll do later on. But just notice that we call this a truss. Okay, this is a truss, T-R-U-S-S, a truss, kind of like the side of a bridge. And they also hold up like maybe the roof of your house, like up in the attic, there's a whole bunch of these. And so we have to label the lengths if we know them and the angles if we know them. Free body diagram practice. So this says, create a free body diagram for the children's sled pictured below. Now again, I recommend that you watch this slide like this because it'll walk you through it. So, okay, so of the sled. So here's the sled. I know that gravity's pulling down on the sled. Gravity's pulling down the sled. So they've labeled that W for weight, which is fine. Weight pushing straight down, right? Gravity on the sled. I know that there's an equal normal force because they're not falling through the snow. They're also not floating up off the snow. So whatever's pushing down, the snow is pushing back up. Okay, so normal force. And again, that's not incorrect, right? They could have put this the W up here, but they didn't. They said, hey, in the middle of this object going down because gravity is affecting the middle of the sled. Okay. And then there's some applied force, like something is either this is tied to a horse or a bike or a skier or a mom and dad or a big brother and sister who's pulling this sled. So there's an applied force in this direction. Do we know what angle? No, but we can label that with an unknown, right? Theta is, there's an unknown angle there. So we have weight pulling down on the middle, a normal force pushing back up on the middle, both equal. We have some kind of applied force in a diagonal, but we don't know the angle. And then we have the force of friction. So we have the sled is being pulled to our right, but it has friction going back to the left. Now, the important thing to notice here is that this arrow is shorter than this arrow, right? Because the sled is going, it is moving. So it can't be pulling back harder than it's pulling forward because then the sled wouldn't be going forward, right? Okay, so here's our ramp idea again. So create a free body diagram of the refrigerator. So again, in my mind, I'm picturing circling just the refrigerator, right? So if I redraw that, there's the refrigerator. Gravity pulls down on the middle of everything. The normal force has to be perpendicular to the base, like I said earlier, perpendicular to the base. The man is also pushing on the refrigerator. So over here on the box, something is pushing on it. We don't know what angle it's pushing, but certainly something is pushing up on the box, right, on the refrigerator. So remember, a free body diagram is a diagram of all of the forces acting on an object. Here, the object is the refrigerator. So we need to know all of the things acting on the refrigerator. So far, we know gravity is pulling it straight down. We know the ramp is pushing it back up. We know that the man is pushing it up, the worker is pushing it up the ramp. Okay, so and then by pushing it up the ramp, there's friction coming back this way. So we know that. What we do not know is the angle, though, right? We don't know what angle the ramp is, right? We don't know what angle the ramp is. Okay? Okay, so create a free body diagram practice. Okay, so this is a pulley system. The important thing here is that ropes and chains are replaced with tension forces. So we'll get there in a second though. So this says create a free body diagram for the pulley system pictured below. And it says of M1. So M1, it's not resting on anything. There's M1. So it's not being supported down here by anything. So there is no normal force. We have the weight of M1. So this thing has weight. Tension. So cables, ropes, and chains are replaced with a force called tension. Okay, movable pulley has something pulling down on it, gravity, and this. And then it has two cables pulling up on it. So that would be our free body diagram there. Okay. So here, these are some vocabulary things you're going to have to know. So cable, ropes, and chains are always replaced with tension. Always with tension. So we have the weight of the object pulling down, and we have, so gravity is pulling down on this object, right? So we have gravity pulling down, and the cable is pulling up. So the cable is pulling up on it. And I'm going to let you go through these. Okay, so important vocabulary here. This picture is a symbol that stands for a pin support. And what you have to know about that is that it represents a force. So this is a symbol. Symbols represent things, right? The American flag is a symbol of freedom. So it is just a symbol that means lots of things to lots of people. Well, this is a symbol that means something, right? So when we replace the symbol and we draw a free body diagram. So if I said draw a free body diagram of member A, right? So I would basically be circling A in my brain, but then I'm going to replace the symbol with the actual forces, right? Free body diagram. So draw a diagram of A and all of the forces acting on it. We assume that it is a positive force for now. So my X force is going positive and my Y force is going positive, and they're reaction forces. So really, the way that I like to label those, okay, the way that I like to label those would be, so we have member A, right? They told us we have member A, and we had a pin joint, a pin support. So if we drew a free body diagram of that, we're basically saying, okay, let's picture this, right? Okay. All right, so there's A over here, all right? Member A, and where are all the places something's, something's going on here, so something's going on here, but we're going to replace this with a force in the X and a force in the Y direction. And I like to refer to those as R, A, X, and R, A, Y. Okay, so that is a reaction force. So reaction force in X. Well, actually, let me back up. It's going to be reaction force. Let's say it in order. Okay, so reaction force at point A in X direction. And we assume it's positive for now. And then this reaction force at point A in Y direction. Okay? So that's how I like to label that, RAX or RAY. Sometimes people will say RAX, RAY. I like to do it RAY, RAX. Okay? All right, so when we go back to so that's a pin joint. Now the next slide shows you a roller joint, okay? And a roller joint, so if this is a roller joint is round, so that's easy to remember, right? Round things roll. And sometimes, by the way, you might see this drawn like this. Sometimes you might see it drawn like this. Right, so it's got wheels on it. So that's how you remember it's a roller joint, not a pin joint. So this is a roller joint, and roller joints, or roller supports, I should say, roller supports, okay, are replaced with a force in the perpendicular direction. So if I were to draw a free body diagram, a point of member A, here's member A, and I'm going to replace this with a force in the perpendicular direction. And because it's underneath, then that's where I would draw it. Okay? And I would say reaction force at A in the y direction. It's perpendicular is important because what if it was like this? Or what if it was like this? Okay? If it was like this, then I would draw my beam and I would draw it perpendicular. If it was like this, I would draw my beam and I would draw it perpendicular. Okay, so perpendicular is important for roller joints, not in the y direction. In this case, it happens to be in the y direction, right? But it is perpendicular to the surface that it's on. So this would be RAX if we had it pictured like this. And generally, you're not going to see anything in here that is like this. Okay, so focus on these two examples here, but just realizing that it has to be perpendicular. Okay. Okay, so RFAX, so they do RFAX, which stands for reaction force at point A in the x direction. I cut out that F and I just say RAX. Okay. A roller joint, perpendicular. Okay, it says perpendicular to the surface. Okay, and we will get to this shortly. But if I said draw a free body diagram of member AB, right? So I have to draw my member. I have to label things that I know. I know that there's some force pushing down on it. I do not know what that force is, so I don't label it otherwise because I don't know what it is. I have to label it in the right location, going in the right direction with the right magnitude. So right location, right direction, right magnitude. So there's something affecting this beam pushing down on it. I replace the pin with an X and a Y, and I replace the roller with a perpendicular force. So this would be the long version of this, right? This just has a bunch of symbols. This would be the free body diagram of this. Okay? And then the last one is a cantilever. So what I want you to imagine for a second, this says that it's a wall, right? So what I want you to recognize, so let's go through it first and then I'll give you an example. So there's something pushing down on the end of this beam. So we have a wall and we have a beam sticking out of that wall. Okay? And you might have this at home. You might have a shelf that sticks out of the wall and isn't supported by anything underneath. It's just attached to the wall. But you have something out here sitting on the edge of the shelf. So it's pushing down on the edge of that. So we draw a free body diagram of basically this object. They call it a cantilevered object when it's hanging out like that. So this is always going to be the case. We have a force going that way, a force going that way. We have to label this because it's given in the picture, but we're replacing the wall with a force that way towards the object, a force up on the object, and a rotational force. Why does that make sense? So quickly, I'll explain that, right? So let me go back over here. All right, so basically they had something like this. And they had an object sticking out like this, right? And they had this. So we're drawing a free body diagram, basically, of what's going on with this thing. Like, what are all the forces acting on that? And what I want you to imagine is, I want you to imagine, instead of this being a wall, I want you to imagine that this is a person. Imagine that this is a person, right here, person, right? And I want you to imagine that they're holding a stick out in front of them, right? A long pole out in front of them. And that pole weighs 10 pounds. Okay? So it's heavy, right? It's because it's long. So what's happening is what's happening to this bar to keep it up in the air, the pole. Well, clearly the pole is attached to the person, so the pole is pushing in towards the person. So what must the person do back so that the pole doesn't go through them? Well, they react by pushing back. And the pole is 10 pounds, so it wants to go down, right? It wants, if this person lets go of it, they just open their hand, what happens to it? It falls straight down. But it's not falling straight down. Why? Because the wall, or the person's hand in this case, is pushing up here, right? If they let go, it's going to fall down, which means, okay, the pole's not going through the person, so that means the person's pushing back out on the pole. The pole's not falling down. That's because where the pole touches the person, it's being pushed up. But this pole also wants to do this weird thing. Let's say that the person kind of held on to it, but held on to it loosely. What would happen? Well, this end would fall to the ground like this, right? It would just swing down in front of them. But it doesn't do that. It's sitting there. It's not moving. Why? Because at the person's hand, they're also spinning it in this direction. They're spinning it in the opposite direction. Okay? So at their hand, right, the pole wants to go in, so the person pushes out. The pole wants to fall down, so the person's hand pushes up. The pole wants to fall this way, so the person's hand pushes this way. Okay? So that's the hand pushing out, that's the hand pushing up, and that's the hand twisting it so that it doesn't fall down. So all of these things are happening right here so that this thing just stays sticking out. And that is a cantilevered support. It always will have a reaction force in the X, a reaction force in the Y, and a moment force. In this case, that's symbolized by a counterclockwise moment. Okay? All right, I'm going to pause there, and we will cover some more in class as well on Friday. So thank you very much for tuning in to this video.